Okay, so good morning, and today we will continue our study of the Grand Canonical Ensemble. And I made a sign error last lecture, so I just want to quickly spend a minute or two correcting it. And so I'm really sorry about it. So this was the thing where we said that there's a reservoir which can supply both energy and particles, and so our system had energy E1 and N1, and so we sort of expanded, did a Taylor expansion about of log omega 2, which is a reservoir, about this thing, and so I defined. So we defined beta here, and then I defined beta mu, but it turns out that this is not plus beta mu, it's minus beta mu, and so the error propagates, but it's just this error. And I sort of fixed it by saying z equal to e power minus beta mu nu, which is a fugacity. But but that is because I had this thing in my head. I always make this mistake of thinking of z as e power minus. Z is e power beta mu. Okay, don't make my mistake again. So I'm just making. So it's just a sign which propagates. And you can see that I wrote this, and so I identified whatever was inside this bracket with z, but that's what it should. Okay, so I corrected. So again, there's one more error here. So z is the fugacity. So after that, I believe the rest of the things are okay. So I'm really sorry, but I have made the same mistake before. It's kind of very funny. It sort of makes me angry at myself, but I think one should be forgiving. Okay, so are there any questions and comments about that? Hopefully, you're able to sort out those things. And if you looked at any standard textbook, of course, it will be given correctly, unlike my last lecture. So the agenda today. So the agenda today is to sort of discuss the types of particles in nature, and rather types of statistics. Okay, so this is the thing which I would like to discuss, and so we will see that there are two types of statistics, and we'll just call them Bose and Fermi. Okay, and so let's look at it, what it means from the viewpoint of quantum mechanics. And so the first thing is we have to understand is the notion of identical particles. Okay, so suppose we have two dogs. Let's say they're the same breed, they're very identical. Okay, but we can give them two names, and after some time we can see if they're twins or whatever. How to separate them out. But suppose we have a system which has say only two identical particles. Okay, and then we might think we can do the same thing. We can name particle, can call them particle 1 and particle 2. But the point is that there is a quantum mechanics introduces a limitation in the accuracy of measurements. Okay, and this is sort of follows from, for instance, from the uncertainty principle, for instance. So this is not it's not a limitation of your instrument, right? So suppose you wanted to measure some length, you had a ruler which had only centimeter. These things you can measure only to up to half centimeter maybe. But if you give it extra gradations, you can a millimeter you can do. So you can improve accuracy. and that's like changing the measuring instrument. But the limitations which quantum mechanics imposes is fundamental, and it cannot be gotten rid of. Okay, this is something to remember. Okay, so the idea here is, let us just go ahead and say that there are two particles, 1 and 2. Okay, so these are quantum particles, and the thing is that they are moving around, and so let's say that we have a process where they enter this way and they come out this way, and this, let's just write something like that. So this is the thing, and this blob out here just tells you they have certain momentum, so they really you cannot localize them beyond some distance, that you know that. Okay, so 1 and 2 are not stationary; they have some momentum. So we are so there is some imprecision, and so the ball indicates the imprecision, if you wish, in spatial. So I should have drawn, if you wish, instead of a single line, I could have drawn a thicker thing. But I in the spatial location of a particle, of the particle. Okay, so they are coming quite close to each other, and such that the uncertainty blobs overlap. So there is some region, and so now the question to you is, I've written 1' and 2', and this is where the thing is, which one is 1 and which one is 2?
So
We cannot distinguish. That is what happens, because there are two different processes which could have happened. So we could have had a situation like this, and this is the blob I'll draw again. We could have had this happen, or we could have had this, them go through each other in some sense. Okay, so both can happen, and so what is happening is that so here this is, we'll call this this is direct kind of thing happening, and this is an exchange. Okay, so of course, if they were two distinct particles, suppose it's one of them is an electron, the other is a proton, we can tell them. Then we can distinguish between whether the exchange happened or the direct happened, because there are other quantum numbers that we associate with them which distinguish them, right? So, but here we are assuming they are identical particles. Okay, so did I say that here? Okay, so let's say it itself, 1 and 2 are identical particles. Okay, so we can so the thing is that so this is the the conclusion is that we cannot distinguish between particles. Okay, and so the thing is that so for instance, here we can think of this exchange as some kind of statistical interaction where they get exchanged. So we can think of this as some statistical interaction. Okay, so now let us suppose we have n particles Okay, there can be the various exchanges are given by elements of the permutation group of n objects. Okay, so the statistical interaction will tell you that they go this way, that way, and so I'm just saying that this generates the permutation group. Does anybody have any questions about this statement? No comments?
So if you could explain a little bit more.
Yeah, but no, you know what the permutation group is, right? So let's go back, and now I'm going to do that. I'm going to do that in a moment. So we can call this where they get exchanged as some operation P12. That's the 1-2 exchange. Okay, is this clear? They are getting exchanged in some sense, and this we can think of as identity operation. Okay, so Sn, so this group is generated.
So
Yeah, go ahead.
what is exchange and what is direct is convention, right?
What is a convention? Nothing. I mean, P12 is just the operation which exchanges 1 and 2. That's it.
Okay. Then what I'm saying is like in that diagram, what is direct?
Yeah.
and what is
Yeah. So direct means one is equal to 1 prime, 2 equal to 2 prime. Okay. So I started off with this blob. Okay, and so there are two possibilities. One is equal to 1 prime and 2 is equal to 2 prime. Other possibility is 1 equal to 2 prime and 2 equal to 1 prime. I'm calling the one which with this kind of thing I called it exchange because they get exchanged.
Yes, sir.
Okay. The group, this permutation group is generated by elementary pairwise exchanges. Any element. Okay, so we could start like this: P12, P. You can see that I can have P23, P14, so on and so forth. But okay, so this all of them you put together. In fact, you can do the following thing: that you can. It's a minimal set is actually even simpler. It's just I think P12, P23, blah blah blah, Pn and -1. These generate all the required. Okay, so these are how many generators? I guess they are n generators. Okay, so this is a minimum set. Okay, so mathematicians will write Sn is equal to generated by they'll put this square bracket. Sn is just the permutation group with n objects. Okay, with n particles. So let us just look at any. So it suffices. So let us look at the operator P12. Okay, what is P12 square? That means we operated 2 times.
1.
Okay, it's identity. No x. Okay. So this implies that the eigenvalues of P12 are, what are they?
Plus -1. Plus 1 and -1.
Okay. So now we will now we are sort of ready to define those statistics. Okay, so the more statistics are where so this p12, so we can we can have an n particle wave function. So psi at x1, x2, xn. Okay, so this is the wave function of n identical particles. Okay, located at okay. So we'll start with spinless particles. If there is spin, we have to add this thing. I'll do that in a moment. But let me just, for practical purpose, just write something like this. So P12 acting on psi x1, x2, so xn will be equal to psi exchange x2, x1, but do nothing to the rest. So let me use a different color actually to show the exchange. Okay, so this is just the action of P12. It exchanges this thing. So let me just do. Let's add additional quantum numbers. Okay, so if sigma is some spin quantum number, then we can write a wave function which is x1 sigma 1, x2 sigma 2, xn sigma n. Okay, and p12 acting on this will be equal to, why did I go to yellow? So now I have to switch to white. So now what should I write? Someone tell me what is the operation of p12?
Oh, x2 sigma 2.
Yeah, absolutely right. So the key here is that all the quantum numbers, all the attributes should be x2 sigma 2, x1 sigma 1, and the rest will be the same. Okay, so we say,
Sir,
yeah,
is it still the same operator?
is it
Is it still the same operator?
p12? Yeah, it's just exchanging the particles 1 and 2. Okay, I mean, so I added an extra quantum number just to say that it's not just x, we have to exchange every attribute. If it had 5 quantum numbers, you have to exchange all 5 of them, every particle. Okay, so we say that set of particles satisfy those statistics if p, let's say ij, acting on psi, I won't give the right thing, is equal to plus 1 of psi. Okay, so plus eigenvalue is chosen for any. Okay, of course I not equal to j. Fermi statistics acting on the wave function is equal to, what should I write here?
Minus.
That's it. Okay, so uh, so we say that the wave function n particle wave function is totally symmetric or antisymmetric for Bose, for me, particles or let me
So
write.
for both case, we can take I equal to J, right?
What?
For both case, we can take I equal to
No,
J.
no, no. What do you mean exchanging something with itself? It has no meaning.
It'll just be identity.
No, no, no. I mean, they call it identity. Identity exists even when it's not. It's not that. No, we don't define it. There's no. It is defined only for I not equal to J. Okay. Other case, it's called identity.
So even if it is minus I, none of the expectation values are going to change, right?
Yeah, yeah, but there are some properties. Even if you think about but for instance, some properties when a minus sign will show up that if two particles have the same set of same quantum numbers, it will vanish. The wave function vanishes, right? So so there is a difference, and it makes a difference. Okay, so for particles satisfying those. Okay, this is something which we want to. So this is just defining this. Okay.
So will you show the post statistics definition again?
What?
This definition I did not see.
So we saw that the p eigenvalue, pi12 or any pij, it can have eigenvalue +1 or -1.
Okay, sir.
Okay. So here I'm saying that it is necessarily in a +1 eigenstate for both statistics, and it's necessarily in a this. Okay. So now what I want to do is recall our second quantization story. We wrote the wave function as something like this, right? For a spinless set of particles, we have n of them. We constructed this n particle eigenfunction, and we saw what was the property of. This was in the problem set, right? Okay. What was the property of this side? Huh? It was totally symmetric. Okay. So clearly, and the key point was that what we had was something like this. Let me just add some other. We didn't have sigma previously. I'm just putting that by hand. And some Chronicle delta. And the other ones commute. So this was the thing, that there was an anti-commutator, and from that thing, so all the A daggers commute with each other. So that implies that psi is necessarily symmetric. So you can see that with this kind of creation and annihilation operators, we can only construct for you totally symmetric wave functions. Okay, so we don't have to do anything special. Any psi you put in there will necessarily have to be totally symmetric. Okay, so this is for Bose. Is this clear? Hello?
Yes.
Okay. So now the question is, how can we do what is, so now this will bring over the question, what is the second quantized version of Fermi system? And the answer is very simple. Okay, so replace commutators by anti-commutators. Okay, so what do I mean by that? So I use this kind of bracket. Okay, this is called an anti-commutator. Okay, so then, so so the we'll call these fermionic oscillators. Calling them an oscillator is a little bit of a loose usage, but fermionic oscillators will
Sir,
satisfy. Yeah,
the above expression is that computation is equal to delta of x plus x prime, but it is supposed to be 0, right?
A dagger is not supposed to be zero. A is zero, A dagger is zero. I wrote only the non-zero guy. There are two more sets to write. If everything is zero, there is nothing there.
Okay, so
So it's like go back to the harmonic oscillator where there was none of these x and sigma and all. A dagger was one, no? Commutator.
yes.
Okay. So this will go like this. Okay. So this is what it says. Is this clear what I've written? So let us do a little bit of a toy model instead of having continuum. So let's do a toy system with discrete variables. So we'll just write something like this. Okay, and let's say that I goes from 1, 2, 3 up to some little n. Okay, so we have n straight-head oscillators, and we can try to construct the Fock space like we would do, right? So focus on I equal to 1 for a moment. What do we get? We get B1 dagger equal to 1. But these things don't have extra things. So you look at this thing, it says that B1 is what? What is anti-com? Is 0. This is also 0. So now if you say that, let's say we define vacuum, to B1 annihilated by all the BIs. So the definition of vacuum, no particles. Okay. But now if you try to do this, so you can do, so you start with this, focus again on B1. So I can do B1 dagger of 0. Okay. What about, can we apply it 2 times? Why is it 0? Because of this. Okay, so what it says is that with, you can only create one oscillator, only one excitation can be 0. So what we get is that we will get the, we'll call this a Fock space. It's finite dimension. And what is its dimension?
Number of particles.
With dimension 2 power m. So let's understand how this works. So B1, I can, so I start from the vacuum, I can apply B1 dagger only once. Okay. Next I can apply, so let's look at this. So one particle, so we'll have 0, but then we will have B1 on 0, dagger on 0, B2 dagger on 0, so on and so forth. Bn dagger on 0. This is the one particle state. But now two particle states will necessarily be of the type B1 dagger, B2 dagger. I can't have things like this. So how many of, so there are one of these guys. Here there are n, and here they have to be antisymmetric. They have to choose different ones. So there will be NC2 of them. Okay. Similarly, there will be things like B1 dagger, B2 dagger, R types. And how many of them will be there? And the maximum we can do is an M particle state, right? So the topmost fellow will be B1 dagger, B2 dagger, dot dot dot. How many states are there of this type? Just one state. Okay, so I will use the same as identity. 2 power m is equal to summation r equal to 0 to m choose r. Okay, so where r is the number of r particle states that you can construct, and with these things, this is all you get. Okay, now let us just look at this. Let us look at a two particle state. Okay, so now you look at this. What is the anti-commutator of B1? Okay, this is equal to minus B2 dagger, B1 dagger. Why? The anti-commutator of those two guys is 0. So if I take this to this side, it becomes a minus. Okay, for bosonic oscillators, it didn't matter, right? If I took A1 dagger, A2 dagger, I take it through, it will get no change in sign. So there is nothing. So so antisymmetry is being enforced. I'll pause here for some questions understand what I'm saying? So coming back to this original story, it is these guys which have, weight. They also mean something. The analog of this, rather this line here, these have meaning. These reinforce the antisymmetric properties. It says that if you have only m of them, the Hilbert space is finite dimensional. Okay?
Sir,
Yeah.
what is A and B?
A was defined earlier. I just defined it with this. This is the A for the Bose statistics, whatever we had done in the assignments.
Okay. So this is the definition of A,
Yeah.
right?
So I just used a different letter B for the Fermi guys
Okay.
because they satisfy different relations. So these are fermionic oscillators. Okay.
So
So
dagger means conjugate or
yeah, conjugate, Hermitian or joint or whatever. Okay. Yeah, these are quantum mechanical operators. Okay. So now we can write. I can write a psi, which will be again like before, d cubed x1 xn. Let's also write summation over sigma 1 blah 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 sigma n. These are the spin variables. Okay, so then we can do this. B Okay, so now I've got for you. So this exercise or easy thing, it just follows from what I said because these now the ordering matters. So I have to write. I've written it in a particular way. Exercise. Show that psi defined above is totally antisymmetric. Okay. So now you can see that we can have a particle description which automatically the statistics is encoded in the anti-commutation relations now. Okay. So what we see is that Fermi and Bose statistics are realized very nicely in quantum mechanics in this fashion, in second quantized version by having bosonic oscillators and fermionic oscillators, and that's it. Okay. So I'll pause for a second for questions, and then I just want to mention one important theorem which is not relevant for us, but it's like general knowledge. Any questions, comments? Okay. So let us. So I just want to tell you something called the spin statistics theorem. Okay. So what it says is that particles with integral spin, satisfy both statistics. And half integral That's what it says. Very simple. Proof is not so simple, but okay. So the proof comes from quantum field theory that if you try to create fermions with integral spin, you get nonsense, if you wish. Okay, so this is some beautiful story. So spin can be 0, 1, 2, 3, so on and so forth, and these statistics will be half, 3 half, 5 by 2, blah blah blah. The statistics will be 1. Is this clear? So this is something worth remembering. Okay. So I'm done with today's lecture. So just I wanted to tell you that the idea of second quantization, it connects up nicely with the possible statistics, etc. And but for instance, there are other things called anions and stuff like that, which are other statistics. But I don't think we have a proper field theory of those things. Okay, so from the viewpoint of quantum field theory, these are the only possibilities. Okay. But anions do occur, anionic statistics, which is other statistics. But at our level, we'll work with something very, very simple. Okay, I'll pause here. Questions?
Hello, sir.
Hello, I can't hear you.
Yeah. Can you hear me now? Hello.
Yeah, yeah.
Yes, sir. I wanted to ask, it's a very okay. So, when we solve a Hamiltonian and we obtain energy eigenstates of the Hamiltonian, so for different energy eigenstates, we can have some transition and then we can relate those energy eigenstates. And
Yeah.
but here, when we have a permutation operator, we are getting the same. We have the same eigenspace sign,
Yeah. So
and then we are getting different eigenvalues with the plus and minus one.
yeah. So actually, that's
Can
a
we
yeah.
relate?
So you're asking what about the interactions, etc. So if you remember, we were writing
Yeah.
Hamiltonians, etc. So the point is that the Hamiltonian will be always symmetric under exchange. So if you go back and if you remember how we acted on things, so what you so for instance, I wrote a potential, if you remember, V of x1, x and y. Okay, you can check that the way it is written, it follows whether it doesn't matter if it is Bose or Fermi statistics. V of x minus y will be symmetric under exchange. So V of x vector minus y vector will be equal to V of y vector minus x vector. Okay, so the Hamiltonian will be symmetric both for Fermi and Bose particles. That's all you can say. Okay, so I'll maybe write something. So what I'm saying here is, if you have a Hamiltonian, it's an operator, right? So P will come 2 times. I could have written P12 dagger, but P12 dagger is P12. So just write this. Okay. So in the second quantizing, you can even prove this part, that the Hamiltonians that you would write would be if they involve just exchange of particles, etc. So if you have interparticle interactions, they will necessarily be symmetric. Okay? That's a very nice question, Bhajan.
But sir, I'm still not clear. I'm saying for this.
It's like you're garbled. I don't understand what you're saying.
No, it's like I'm still a little confused about it. I will have to think.
Okay, you can ask again. You think about it. Look at the previous problem set, and then we can take it from there.
Yeah.
Okay?
Okay. Yes, sir. Thank you.